Mine that way. There is a question to work on while I try to make this look better. Hmm. All right, get started. I'm mildly annoyed because usually this little bar thing here will go away if I put it at the top. But for whatever, whoops, that's interesting. Okay. No, still no dice. I don't know why. It won't disappear like it usually does. This will just live there for today. All right, so let's get started. Co-17A. Today is May 6th. Yeah. So sometimes you see a question like this, where in fact, usually they kind of leave off these first two parts and say, calculate the limit as h approaches 0 of 2 plus h cubed minus 2 cubed over h. And the idea with something like this isn't to actually multiply it out and cancel things and factor out the h and divide out the h and then take the limit. The idea is to recognize that this is the limit definition of the derivative of some function, and then just take the derivative like the easy way. So here I see my f of x plus h cubed minus my, well, I should say my f of 2 plus h being 2 plus h cubed, my f of 2 being 2 cubed. So it looks here like my function f of x is just the function x cubed. Because if we're taking f of 2 plus h and getting 2 plus h cubed, oh yeah, it's whatever your input is, just cubed. To answer the rest of the questions, we're going to do it the fast way. We're not going to do the limit definition of the derivative to find the derivative of x cubed. We're going to use the power rule and say, all right, cool. F prime of x is 3 times x to the 1 less power. So 3 times x squared. And then finally, and I would say that these are kind of like intermediate steps. Like if you're actually asked just this question, you would kind of do all this to the side or in the background and then say, okay, I know my function's x cubed. I know the derivative is 3x squared. And then when I plug in 2, my f prime of 2, which you could write this way, One of your instructors was also pointing out that another notation for this would be df dx evaluated at x equal to 2. They mean the same thing, it's just different notation. Either way, that's going to be 3 times 2 squared. You have to do the squaring first. That's 3 times 4, which is 12. It's not fancy for that question. To get that question. It tests your understanding of what the limit definition is, as well as your ability to find the derivative using whatever kind of shortcut rules we talked about. All right, let's continue talking about the stuff we were talking about last week, which was the product and the quotient. So as a reminder to everybody, and please let me know if I get off screen here in some way. The product rule said that if you want to take the derivative of f of x times g of x, it's equal to the derivative of f of x times the not derivative of g of x, plus then you switch it. The not derivative of f of x times the derivative of g of x. Or as I like to say in my head, each derivative gets multiplied by all the other functions. So the derivative of f gets multiplied by g, the derivative of g gets multiplied by f. If there was 3 functions, the same sort of thing would happen. We talked about that last time, how you have a triple product rule or a quadruple product rule or a product rule for any number of things where each single derivative gets multiplied by all the other left alone functions. You get all those things happening. The quotient rule looks similar, kind of. Actually, the reason I say it looks similar is because to me it looks like the product rule divided by g squared, except you're switching the sign from plus to minus. So the quotient rule is saying that the derivative of the quotient f of x divided by g of x is f prime of x times g of x minus f of x times g prime of x, all divided by g of x quantity squared. Or as I say in my head, you might want to watch this for a second, I do the g part first. I say it's the bottom times the derivative of the top minus the top times the derivative of the bottom multiplied by the bottom squared. Same thing, we can always change the order of multiplication, it doesn't matter, but we do have to keep the order of subtraction as is. You can't put that over there and that over there. So let's look at some examples. I know we did a few last time, but there's a few more I want to do. So let's start with finding, say, for f of x equal to x cubed times e to the x divided by x to the 4th plus 1. Let's go ahead and find the derivative. There we go. So I see actually both things happening here. We have a quotient, we have something divided by something else, but we also have in the top part a product of 2 things. So I would kind of think of this as the quotient first. I'm going to write this out as giving me the derivative equal to, I'm just going to say the words, the bottom times the derivative of the top, which we'll get to in a second. So for now, I'm just going to write x cubed times e to the x prime minus the top times the derivative of the bottom, x to the 4th plus 1 prime, all divided by the denominator squared. But now we actually have to go and take those derivatives that are written in there, right? It's the bottom times the derivative of the top part. Well, now we need to find the derivative of the top part using the product rule. So writing this out further, we're going to have x to the 4th plus 1 multiplied by the derivative of the product of x cubed times e to the x is, okay, it's the derivative of the first thing, 3x squared, times the not derivative of the second thing, plus, and then we switch it. We leave the first thing alone, so x cubed stays as is, and we multiply by the derivative of e to the x, which is e to the x. So we are taking a derivative here, even though it looks like we've done nothing. Close that bracket. Continue on. Minus x cubed times e to the x times the derivative of x to the 4th plus 1, which is 4x cubed, divided by x to the 4th plus 1 squared. Could we do more? Sure, we could multiply this out and simplify. Do we need to do more? Not really, unless we're being specifically asked to, or if we're asked to say, like, find where this function has a horizontal tangent line, and then you would set the derivative equal to 0 and solve for x. Yeah. Totally, yes. So if I'm thinking of my x cubed times e to the x as my, say, we'll call it a u times a v, and now we're taking the derivative of a u times a v, then we're getting the derivative of u times v left alone plus u left alone times the derivative of v. And it's a little bit confusing because, right, the derivative of e to the x is just e to the x, so it kind of looks like we didn't do the thing even though we did do the thing. But sometimes you can have a product for one side, a quotient rule, or vice versa. Sometimes you could have a quotient rule inside a product rule. For example, if I said find the derivative of, say, x to the 7th plus 2 times sine x divided by e to the x. Now we're going to use the product rule and the quotient rule, but now the product is kind of the outermost thing we have to deal with first. So our derivative is going to be, and this is where I would, again, you don't have to label things, but I'm going to label this as f and as g so I can kind of keep track. Okay, my product rule is going to be the derivative of f, which is 7x to the 6th, times the other thing left alone, sine x divided by e to the x. Plus, now we switch. We leave the first thing alone, x to the 7th plus 2. And since taking this derivative is going to take a little bit more work, I'm just going to write sine of x divided by e to the x prime. Telling me, okay, I still have to take that derivative. So now I've got exactly my product rule. My derivative of f times g left alone plus f left alone times the derivative of g. But now, just like in the previous part, if we have some primes left in what we've written, we still have work to do, right? That's telling me I still actually have to find that derivative. So let's continue on. We're going to rewrite all of it and get 7x to the 6th times sine x over e to the x plus x to the 7th plus 2 times, okay, quotient rule here, it's the bottom times the derivative of the top, derivative of sine of x is cosine of x, minus the top, which is sine of x, times the derivative of the bottom, which is also e to the x, divided by the bottom squared, which is e to the x squared. If you wanted to, you could definitely write the bottom as e to the 2x, because e to the x squared is just e to the x times e to the x, which is e to the x plus x, which is e to the 2x. But again, most of the time, we're not really trying to simplify these things. We're just trying to do the work of having taken the derivative, then we're going to stop. It's not trying to test our ability to simplify. It's testing our ability to find the derivative. Unlike the next problem. So our next problem asks the following. For what values of x does the following, f of x equal to x squared divided by x minus 1, have a horizontal tangent line? So what's special about a horizontal line? It has a slope of 0. So when we are asked to find where a function has a horizontal tangent line, we're really just kind of hiding the real question, which is we're really asking, where does the derivative of our function equal 0? That's the question we're actually asking. We're asking where we have a horizontal tangent line. Great, we can do that. We're going to take the derivative and then set it equal to 0 and solve for x. All right, so here's my function, x squared divided by x minus 1. And yes, again, we're going to use the quotient rule. So why doesn't everybody try using the quotient rule right now to find that derivative? I'll give you a minute. All right, let's go and see what we've got. So again, if you're saying it how I like to say it, I'm going to write it as the bottom function x minus 1 times the derivative of the top minus the top function x squared times the derivative of the bottom, which is just 1, all divided by the denominator squared. And normally we would just stop there. But since in this case we're trying to set this thing equal to 0 and solve for x, we really do need to simplify this expression as much as possible. So I'm going to multiply at the top. The 2x distributes to the x and to the -1, and we get 2x times x, which is 2x squared, minus 1 times 2x, which is just minus 2x, minus another x squared. And we should leave the denominator alone because the denominator is kind of as simple as it gets. It's factored, it's what it is. There's a couple more steps for simplifying the numerator. We're going to say that 2x squared minus x squared is just x squared. So x squared minus 2x divided by x minus 1 squared. And then finally, we should factor the numerator as much as possible. I can factor out an x, and I'm left with x times x minus 2 divided by x minus 1 squared equal, and we're setting that equal to 0 to try and solve it. All right, so on your fingers, I would like you to show me how many solutions does this equation have? Show me on your fingers. Okay, all right. So let's take a look and see. So to solve this equation, the first step I'm going to take is multiplying both sides by the denominator. So if I multiply both sides by x minus 1 squared, here's what we get. We're going to get x times x minus 2 over x minus 1 squared times x minus 1 squared equal to 0 times x minus 1 squared. On the left-hand side, the reason we've done that is to cancel the denominator because those divide to 1. On the right-hand side, 0 times anything is still 0. So now we're left with the equation x times x minus 2 equal to 0. And that equation has two solutions. Either x could equal 0 or x minus 2 could equal 0, which means x equals positive 2. I will point out that x, oh, sorry, take points of that. I will point out that x equal to 1 is not a solution to this equation. So if you plug in 1 for x, we get division by 0, which is undefined. So, in fact, we can see that graphically. If you look at the graph of this function, we have a vertical asymptote at x equal to positive 1. And it would look somewhat like this. Let me make sure I graph it well here. Yeah. I feel like I'm graphing this wrong. Let me double check my work here. I feel like I'm doing something. Yeah, I think I have graphed it correctly. Let me double. Yeah, I totally did. So let me point out what I did wrong here. I kind of made an assumption that was wrong. I plugged in negative values for x into my original function. If I plug in like 0 for x, well, actually 0, but if I plug in -1 for x, I'm going to get 1 divided by -1 minus 1, which is -2. Or in other words, when I plug in -1 for x, I should be getting a negative output, not a positive output. So this is not what my graph looks like. Sorry about that. My graph actually looks like, see if we can keep this on the page here. Sorry, there's too much paper. So what my graph would have actually looked like would be the following. Still a vertical asymptote at 1. We have an intercept at 0, but it should be going down like this. And the other side should look like this. And that point there where x is equal to 2, we plug that back into the original function, our y value would be 2 squared divided by 2 minus 1, which is 4 over 1, which is 4. And at those 2 points, where x is 0 and where x is 2, that's exactly where we have a horizontal tangent line. Or in other words, which we'll see later on when we talk more about graphing, we found the places where the function has a local minimum and a local maximum. That point right there is lower than all the points next to it. That point right there is higher than all the points next to it. All right. Yeah, might as well add that in here. Sure. So for this function, f of x equal to x squared divided by x minus 1. One more question. Where is this function not differentiable? Well, to be differentiable, it has to be continuous, which means it has to be defined. So there's certainly one place for sure where the function is not differentiable, and that's at the vertical asymptote. Right? The function isn't defined. It definitely can't be continuous. It definitely can't be differentiable. So it is not differentiable at x equal to positive 1. And that's actually the only place where this function isn't differentiable. Every other value of x, you could find the point on the graph and draw the tangent line and find the slope of that tangent line and get some real number. The real reason I'm asking this question is because there's another question I want to ask that has kind of a similar thing that I saw in one of your homeworks, which I thought was really interesting. So, similar question, kind of. Where is f of x equal to the absolute value of x squared minus 9 not differentiable? So I think is an interesting question. The way we're going to see this is by graphing it. So, interesting fact, I don't know, maybe not interesting, maybe it is. To graph an absolute value of a function, here's what you typically do. You graph the function first, so without the absolute value. So just to see how this is going to work, I'm first going to graph just y equal to x squared minus 9. It's your usual upward opening parabola that's been shifted down 9 units. So it looks vaguely like this. It's got intercepts at plus or minus 3. And kind of does this deal here. Now, the problem with this graph compared to the graph we actually need is that an absolute value of some stuff should always give you non-negative outputs. So like when I plug in 0 for x here, I get 0 squared minus 9, which is negative 9. When I plug in 0 here, I get the absolute value of negative 9, which is positive 9. The way we make this graph happen without doing too much work is we take the part that's below the x-axis with negative y values, and we flip it over the x-axis. So here's what the graph that we actually want is going to look like. F of x equal to the absolute value of x squared minus 9. All of this part down here is going to flip over like that. So it's going to look like the following. It's kind of the parabola shape we had before, and coming down like that, and going back up like that. But then the middle part, which would have been down here, flips over, and now it's up here like that. Right? All of the negative y values had to become the corresponding y values, corresponding positive y values. So just to kind of say a little bit more, for example, if I plug in 1 here, I get a coordinate of 1 comma negative 8. because 1 squared minus 9 is 1 minus 9, which is negative 8. But over here for this graph, if I plug in 1, I get the coordinate 1 comma positive 8 because I'm getting the absolute value. And if we look at this graph, I think we can immediately see the candidates for the places where it's not differentiable. We've got some pointy points, specifically at x equal to 3 and x equal to negative 3. So we can see from the graph, oh yeah, this graph definitely doesn't have a derivative that exists where the graph has a cusp there or a corner. So this is not differentiable at x equal to negative 3 and x equal to positive 3. And if anyone ever just gives you a graph of something, you know to look for the places where it's not differentiable by looking for where it's pointy or where it's undefined. So I just thought that was kind of a good question. Also, this graph is kind of funky looking, right? It's something totally graphable, and the absolute value of something is really not too terrible to graph once you realize that anything that's below the x-axis just gets flipped back over. I should say the better math word is reflected back over the x-axis. All right. Let's continue on. So we're going to add to our catalog of functions we know how to take the derivative of. So far, we know the following. We know, so known derivative formulas, rules, whatever. Yeah, let's say formulas. So far, here's what we know. Known. We know that the derivative of x to any power is equal to that power times x to the 1 less power. We know that, I should have probably started with this next one, but I forgot about it for a second. We know that the derivative of any constant is equal to 0. We know that the derivative of sine of x is equal to cosine of x. We know that the derivative of cosine of x is equal to negative sine of x. And we know that the derivative of e to the x is equal to e to the x. I feel like what I should have really titled this is functions we know how to differentiate. I'm not talking about the rules like the product rule and the quotient rule, just things we know how to take the derivative of. And the reason I put the derivative of e to the x up here is because I'm leaving myself some space down here to add to my list. Because we're going to add 1, 2, 3, 4 more things here in a moment. Right? Are there any ones I'm missing so far? At least that we've talked. I don't think we've talked about any other things in class we know how to take the derivative of. I think this is it so far. Okay, well, we're going to add to our list. So the first one we're going to add is the derivative of tangent of x. And the way we're going to find the derivative of tangent is by using the quotient rule. We're going to write this as the derivative of sine of x divided by cosine of x. I should point out, when you're simplifying something, but you still have yet to take the derivative, if you're writing the derivative this way, which is how I usually prefer to write it, you keep writing the d dx because you still have yet to actually take the derivative. Right? Like I say, you keep writing the instructions for the thing you're going to do until you actually do that thing. Just like when we're taking a limit, we keep writing the limit every time until you actually take the limit by plugging in whatever x is approaching, typically. So if you haven't done what the instructions have told us to do, we keep writing those instructions down. But now we're going to do it. We're going to use the quotient rule, and we're going to get the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Okay, we're gonna actually take those derivatives now, so we're going to get cosine of x times the derivative of sine is cosine of x minus sine of x times the derivative of cosine of x is negative sine of x. And I want to point out something about what I've just written here. Yes, I've written minus sine of x times negative sine of x, but when you have something multiplied by something else that has a negative sign in front of it, we really need parentheses around that negative sine of x. Otherwise, the negative can get lost, or if you're trying to type this into web work, it usually will read that as subtraction as opposed to multiplication by a negative. So we're going to say times negative sine of x, all divided by cosine squared of x. So far, this looks pretty ugly. Let's keep simplifying it. Cosine of x times cosine of x is cosine squared of x. Minus sine of x times another negative sine of x is going to be plus sine squared of x, all divided by cosine squared of x. And now we've reached the moment where we need the world's most famous trigonometric identity. At least in my opinion, it's the most famous one. There are others that are less famous. The most famous one, though, is the fact that cosine squared of x plus sine squared of x is always equal to 1 every time, no matter what the angles are. This comes from the unit circle. This is also called a Pythagorean trig identity because it's really just coming from the Pythagorean, it's coming from the right triangle Pythagorean theorem. Just to make sure that everyone is clear with why this identity is what it is, because I imagine many of you have seen it, but some of you might not have. This is coming from the unit circle. And if we look at this angle here, say take an angle of theta, I'm going to use theta instead of x. And this point on the circle here, well, we're going to call it x comma y. And the radius of that circle is, well, it's a unit circle, so the radius is 1. So here's what we've got so far. We can say, well, Pythagorean theorem, x squared plus y squared is equal to 1 squared. But you know what else is true about x and y? They're the trig functions cosine and sine. Because if you look at this right triangle, cosine of theta is the adjacent side, which is x, divided by the hypotenuse side, which is 1, which is just x. So x is equal to cosine of theta. And similarly, sine of theta is the opposite side divided by the hypotenuse. So sine of theta is just y. So you can totally rewrite this equation as cosine squared of your angle plus sine squared of your angle equals 1. That's where that identity comes from. What that means for us is our derivative of tangent can be further simplified. We can rewrite the derivative of tangent as 1 over cosine squared x, but no one actually writes it that way. Since 1 over cosine x is equal to secant of x, we're going to rewrite this as secant squared of x. So all that work to show the derivative of tangent of x is equal to secant squared of x. I will say, it definitely is in your best interest to memorize the derivatives of all 6 trigonometric functions. They will come up often enough that we're going to want to know them just off the tip of our fingers, tongue, whatever, to know them. You want to know them? I don't know. There was an analogy or a saying I was trying to say that I lost, so it's fine. Let's find the other 3. So we'll do cotangent next. We're gonna do cotangent, and then we'll do secant, and I'm gonna make kind of an analogy about how there's a really kind of easy way to remember them by remembering less. So I'm gonna try and make it easy to remember for them for all of them. So let's look at cotangent next. Oh, question, yes. Oh, thank you. Yes, I can. Thank you so much for reminding me. All right, so cotangent, very similar process. The only difference between tangent and cotangent is they're reciprocals of each other. So for the derivative cotangent of x, instead of being sine divided by cosine, it's going to be cosine of x divided by sine of x. So then same deal. Now I'm not going to write out the derivative of the bottom and the top here. I'm just going to actually find them. So I'm going to say it. It's going to be the bottom times the derivative of the top, and the derivative of cosine is negative sine of x minus the top, which is cosine, times the derivative of the bottom. The derivative of sine of x is also cosine of x, divided by the denominator squared. And looking at this, we have almost the trig identity again. If we multiply it out and simplify, sine times negative sine is going to be negative sine squared of x. And negative cosine times cosine is negative cosine squared of x. And in the denominator, we have sine squared of x. And if I factored out the negative 1 from the top, we would have negative 1 times positive sine squared of x plus cosine squared of x, which divided by sine squared of x. And now we can say the numerator here is negative 1 times 1. That's going to be negative 1 divided by sine squared, or more typically written as negative cosecant squared of x. So the derivative of tangent was secant squared. The derivative of cotangent of x is negative cosecant squared of x. There is a pattern, but I don't want to say it quite yet. So we'll do one more and then we'll talk about the pattern, because I think the pattern is definitely worthwhile. So one more, well, actually two more, but one more, the next one. Let's find the derivative of secant of x. So secant is the reciprocal of which trig function? Good question. Sine or cosine? Here's how I remember it. In each reciprocal pair, well, okay, we know for sure which ones are reciprocals. Tangent and cotangent. They go together, right? They're each other's flips. And then for all the other ones, each pair of function and reciprocal function, one of them has to be a co-function. What do I mean by co-function? I literally mean starts with the letters CO. Cotangent, cosine, cosecant. Those are the three co-functions. The reciprocal of tangent is cotangent. The reciprocal of sine is cosecant. And the reciprocal of cosine is secant. Each reciprocal pair has one co and one not co. And we know tangent and cotangent go together. Okay. So secant is just 1 over, which one was it? Yeah, thank you. So now we're going to use the quotient rule for the derivative of 1 over cosine. This one's a little bit interesting because look what happens. We get the denominator, cosine, times the derivative of the top, and the derivative of 1 is 0, minus the top, 1, times the derivative of the bottom, which is the derivative of cosine is negative sine of x, divided by the denominator squared. Cosine times 0 is 0, and minus 1 times minus sine is positive sine. So we're left with sine of x divided by cosine squared of x. And unfortunately, no, not unfortunately, but the truth is no one ever writes it this way. We're going to do two things. We're going to rewrite it as first 1 over cosine x times sine x over cosine x. Want to make sure everyone's okay with that. 1 times sine is sine. Cosine times cosine is cosine squared. So it's still the same. And then 1 over cosine is another name for secant. And sine x over cosine x is another name for tangent of x. So the derivative of secant of x is secant of x times tangent of x. To me, secant always feels like the weird one because most of the time, when you differentiate a function with a variable x, usually that x only shows up once again. This is one of the rare exceptions where whatever you're taking the derivative of, that x thing, that variable, shows up 2 times in your derivative. It's kind of interesting. It's kind of, well, it's unique, except cosecant also does the same sort of thing. So kind of neat. So now here's the pattern I want to point out. Well, first I'm going to write this. Derivative of secant of x is equal to secant of x times tangent of x. So the pattern I want to show you is the following. For the derivative of tangent, we got secant squared. tangent goes with secant squared, and then if you put a co-prefix in front of both of those, instead of having tangent and secant squared, you're going to have cotangent and cosecant squared. So if you know that the derivative of tangent is secant squared, you know the derivative of cotangent is cosecant squared with a minus sign. Similarly, the derivative of sine is cosine. The derivative of cosine is negative cosine, which is just sine, which is kind of where it doesn't work perfectly well, but the cosine is just sine. But then for this last one, it also works. For each of these functions, secant, and tangent, we're just gonna add on the prefix co and a negative sign. So if the derivative of secant of x is secant of x times tangent of x, we'd expect that the derivative of cosecant of x is cosecant of x times cotangent of x with a negative sign in front. And it is. We're going to show it, but it is true. Couple things to notice here, which we'll say again in a minute. Every cofunction, cosine, cotangent, cosecant, all of their derivatives have a negative sign in front of them. The other three do not. Sine, tangent, and secant, the non-cofunctions, don't have negatives in their derivatives. It's a nice thing to remember. Each cofunction, when you differentiate, you get a negative sign. Let's do this last one, though, just to make sure we all believe it, and then we'll go back and fill in that table that I had left behind on my page over there. So, for the derivative of cosecant of x, we're going to rewrite it as the derivative of 1 over sine of x. And then we're going to use the quotient rule again. So it's the bottom sine times the derivative of the top, and the derivative of 1 is 0, minus the top times the derivative of the bottom, the derivative of sine is cosine of x, all divided by the denominator squared. Simplifying this, it's a negative cosine divided by sine squared. Breaking it up into two fractions, it's going to be a negative times 1 over sine of x times cosine of x over sine of x. And then that can get rewritten as negative. That's cosecant of x right there. That's cotangent of x right there. So it really does work. So let's go back and fill in the other 4 trig functions of that table. Make sure that everything's too out of order here. Yeah, okay. So, looking back at this table now, we had the derivative of sine is cosine, the derivative of cosine is negative sine. And there is a very specific way I would encourage you all to write this table. We write sine, cosine, and tangent on the left. So the derivative of sine is cosine, the derivative of cosine is negative sine. The derivative of tangent of x is positive, holy smokes, is secant squared of x. And then to the right of each function, we're going to write its reciprocal function. So to the right of tangent, we're going to write cotangent. The derivative of cotangent of x is negative cosecant squared of x. And then to the right of cosine, the reciprocal is secant. The derivative of secant of x is secant of x times tangent of x. And finally, to the right of sine, the reciprocal function is cosecant. The derivative of cosecant of x is, it's not secant times tangent, it's cosecant times cotangent with a negative sign in front. So I'll say it again. Each cofunction, cosine, cotangent, and cosecant, has a negative derivative. The non-cofunctions, sine, tangent, and secant, are positive. They're derivatives. There's something else I want to say. Okay, so what I would say also about this is you definitely do want to memorize these. For math rules I've wanted to memorize in the past, one thing I recommend doing is taking a picture of it and making it the lock screen on your phone. And then you see it all the time. There was a class I was teaching a few years ago where I had to learn something that was just like, I had to learn what all these like logical equivalencies meant and like the 7 different ways of saying them. And some of them were really hard for me to remember. I made it the lock screen on my phone and look at it every time I had to look at my phone. I was like, oh yeah, I should think about what this really means. So it's not a bad idea. I recommend it. One more thing I'll say here. This is something a student showed me. the way they remember the derivatives of secant, tangent, cosecant, and cotangent. They wrote the following thing. They wrote secant of x, arrow to the right, secant of x, arrow to the left, tangent of x. This showed them, this is totally them, not me. They said the derivative of secant is secant times tangent. The derivative of tangent is secant times secant. And it also works for if you do cosecant of x, negative cosecant of x, cotangent of x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of cotangent of x is negative cosecant of x times cosecant of x. It works. It's not how I think of it, but it certainly has worked for students in the past. So however you want to remember these things, do what works for you. Just make sure you're able to remember them because they are not going to ever go away. I mean, eventually when you're done taking math, okay, but certainly in 17B and 17C, these functions come up. Maybe less in 17C, though, to be perfectly honest. All right, continuing on. So now we have a whole lot of functions we are able to take derivatives of. I'm going to make sure it takes an order here. So where did I want to go next? Sorry, sometimes I get so excited about something. All right. So for example, now we could ask to take, say, like the derivative of x cubed plus 7x divided by tangent x plus x squared. And then we could throw the quotient rule at it and say, okay, well, it's going to be the bottom tangent of x plus x squared times the derivative of the top, 3x squared plus 7, minus the top, x cubed plus 7x, times the derivative of the bottom, which is going to be the derivative of tangent x, is secant squared of x, plus the derivative of x squared is 2x, all divided by the denominator squared. For these problems, it is really important that we use parentheses appropriately. I mean, or I should say, use them if you think you should use them, right? Or don't not use them or if you're unsure. Like, it's always better to throw in more parentheses than not. Because right here, if we didn't write the parentheses around the 3x squared plus 7, it would look like we had just tangent x plus x squared times 3x squared, and then you're adding 7 after you've multiplied. So we really, really, really have to have these parentheses here. The only time you can really get away with not writing them is if you're just multiplying by one thing, and then you don't have to write them, although you still can. Okay, let's look at the following thing. Sure. So I feel like something's really in the way. Don't know why it doesn't want to go away today. It's just interesting. So let's do the following. We're going to use product rule. Product rule, sure. Okay. Yeah. I should say the triple product rule to find f prime of x for f of x equal to x to the 7th plus 1 to the 3rd power, which we're going to multiply. We're actually not going to multiply it out. We're going to express it as a triple product. It's going to be x to the 7th plus 1 times x to the 7th plus 1 times x to the 7th plus 1. So we can think of this as like our capital F, capital G, and capital H for our triple product rule. As a reminder, just so everyone's on board, right? If we're going to find the derivative here, it's going to be each part gets its derivative once and then it's multiplied by the other not derivative. So it should end up looking like the derivative of capital F times G times H plus the derivative of capital G times F times H plus the derivative of capital H times F times G. That's how things should look here if we're using the triple product rule. So let's see how that looks in actuality. So that's going to be the derivative of F is 7x to the 6th times G, which is x to the 7th plus 1, times H, which is x to the 7th plus 1. plus the derivative of capital G is 7x to the 6th times f, which is x to the 7th plus 1, times h, which is also x to the 7th plus 1. Plus, I think the last part's going to look the same. The derivative of h is also 7x to the 6th, and multiplied by f, which is x to the 7th plus 1, times g, which is x to the 7th plus 1. Which I'm definitely going to simplify here so we can see a thing. So, if you notice here, all three of these pieces are the same. So I can really write this, instead of 7x to the 6 times x to the 7 plus 1 times x to the 7 plus 1 3 times, I can write it as 3 times 7 times x to the 6 times x to the 7 plus 1 squared. So I'm going to write it as 3 times 7x to the 6th times x to the 7th plus 1 times x to the 7th plus... sorry, I didn't rewrite it exactly the same way. And now I'm going to rewrite it in the way that is the most useful to me, which is I'm going to leave the 3 in front, but I'm actually going to move the 7x to the 6 to the back. Again, remember, order of multiplication doesn't matter. You can multiply things in any order and not affect the outcome. So I'm going to rewrite this as 3 times x to the 7th plus 1 squared times 7x to the 6th. Another way of thinking about this is if my function, how do I want to say this? Yeah. Here's what I really want to say. So our function f of x is equal to something cubed, or as I will say a lot in the coming weeks, some stuff cubed. And our derivative, our f prime of x, let's see, our stuff was x to the 7th plus 1, so our derivative is 3 times that same stuff squared, but then we multiply by the derivative of the inside stuff, right? 7x to the 6th is definitely the derivative of x to the 7 plus 1. This is an example of the chain rule. If you have a function of a function, we can differentiate that or find the derivative by differentiating the outer function, leaving the inside stuff alone, and then after we've done that step, multiplying by the derivative of whatever the inside stuff was. There's lots of other ways of saying what the chain rule is, but that's really kind of at the very basic level what it's all about. Leave the insides alone, differentiate the outer function, and then after you've dealt with that, multiply by the derivative of the insides. So more generally, I'll say the following. Now, this is kind of not the full version of the chain rule. This is the power rule version of the chain rule. For f of x equal to some stuff to a power, the derivative, f prime of x, is going to be, well, again, if you've got something raised to the pth power, the derivative is going to be p times our stuff to the p minus 1, the usual power rule, but then we have to multiply by the derivative of the inside stuff. Or as someone who doesn't like writing the word stuff might write, if you're trying to take the derivative of some g of x raised to the p power, it's going to be p times g of x to the p minus 1 times g prime of x. But I like saying the word stuff, so I'm going to say that a lot. It's probably the best word in math. So we know the chain rule, or we know the power rule version of the chain rule now. So let's do some examples. For example, if I wanted to say find f prime of x, given that f of x is equal to x squared plus 5x to the 11th power, I could still do it the same way I did the previous one. I could multiply it out 11 times and then use the 11 product rule and write out 11 things added together, but I don't need to do all that. We have the rule now that says, okay, I've got something raised to a power. The derivative is going to be, the power comes down, the stuff stays the same, but the power is now one less. But then what do we have to multiply by? And whenever asked that question, it's almost always the derivative of the stuff. Whenever you've got some stuff to a power, and we take the derivative, it's the power times the stuff to the one less power. We must multiply by the derivative of the inside stuff. I will point out, whenever you're using the chain rule, the original argument of your function, stuff that's inside the function, whether it's being raised to a power, or sine of some stuff, or tangent of some stuff, or e to some stuff, that original argument has to show up again in your derivative. So I just want to make it super duper clear, because I've seen this mistake too many times. I want to point out that the answer here is not 11 times 2x plus 5 to the 10th power. Right? The inside stuff has to get left alone and show back up in our derivative. And then after that is when you multiply by the derivative. Okay, so not you. We don't like you. All right, so why don't you all try this one? Find the derivative of x cubed plus sine of x to the 13th power. All right, we'll start writing it out here. Let's see. So we're going to get 13 times the same stuff, x cubed plus sine of x, raised to the 12th power. And then we're going to multiply by the derivative of that, which is 3x squared plus cosine of x. And I will just mention here, I've written my answer wrong. I'm missing some very, very, very necessary parentheses. If you write it like this, I'm writing it as if it's all this stuff times 3x squared. That's the end of the multiplication, and then I'm adding cosine of x after that. So I must have parentheses there so that we've got the multiplication by the entire derivative of the inside stuff, not just part of it. Let's look at some more examples. So definitely, this is an important thing to practice. The chain rule, basically, for any function, we'll soon see that we know how to differentiate. There's like a chain rule version of the derivative, which we were also going to talk about. Which, we have time for today. Well, let's do a few more examples, which might not seem super straightforward at first, but they are not too terrible. So let's say we want to find for the function f of x equal to the square root of x to the 4th plus e to the x plus cosine of x. We want to find the derivative. And for this example, we should either rewrite it or at least think about how it looks as something to a power. I don't think it's bad to rewrite it. I would rewrite it as x to the 4th plus e to the x plus cosine of x, all raised to what power? What power is the square root? The 1/2 power. So if you're taking the derivative of a root of something, it's almost always in your interest to rewrite it as that something raised to a power. So if it's a square root, it's a 1/2 power. If it's a cube root, it's a 1/3 power, and so on and so forth, right? If it's an nth root, it's a 1 over n power. So in this case, our derivative is going to be 1/2 times all that stuff left alone to the, let's see, my new power is 1/2 minus 1, which is negative 1/2. And then we have to multiply by the derivative of the inside. So it's going to be a 4x cubed plus the derivative of e to the x is e to the x. And instead of writing plus, I'm going to look ahead and be like, oh, my derivative is negative sign. I don't really want to write plus negative sign of x. I'd rather just write minus sign of x. So if you see that coming up, make the smart choice and write just minus the thing instead of plus negative the thing. It's fine to write it the other way. It just doesn't look as nice. So here's what I want you all to try. I want for this one, for g of x equal to, sure, 4 divided by the 5th root of x to the 6th plus tangent of x. Before you start taking the derivative, I just want you all to rewrite this first. Rewrite this as g of x equal to 4 times your stuff to some power. There should be some power right there that I want you all to fill in. So in the denominator, if we didn't bring this up to the numerator, we could rewrite this as 4 over x to the 6 plus tangent of x to the 1/5 power. And then when we bring it up to the numerator, that positive 1/5 turns into negative 1/5. Whenever you move the thing, the sign of the power changes from whatever it was to the opposite sign. So this power up here should be the negative 1/5 power, which I wrote kind of in a weird spot there. Sorry about that. It looks a little funky. But now we can take the derivative. Our derivative, what happens to the 4? Well, it's a constant multiple, so the 4 is just going to hang out. So that 4 sticks around, and then the derivative of some stuff to a power, well, that power comes down, you get a negative 1/5. So 4 times negative 1/5 times our stuff, x to the 6th plus tangent of x, raised to my new power is 1 less. So if I don't know what that is just off the top of my head, I'm just going to write negative 1/5 minus 1. It's correct. It's not simplified, but okay. And then I have to multiply by the derivative of the stuff, which is going to be 6x to the 5th plus the derivative of tangent of x is secant squared of x. And if I wanted to simplify this, which I kind of do, I would write it as negative 4/5 times x to the 6th plus tangent of x to the negative 1/5 minus 5/5 is negative 1 minus 5, or negative 6/5 times 6x to the 5th plus secant squared of x. Not too terrible. Question, yeah. Yes. So I would say I didn't really explain it before. So I will say first, whenever you move an expression with a power from the numerator to the denominator or from the denominator to the numerator, we change the sign of it from positive to negative or from negative to positive. But the reason that's true is because all these exponent things always end up boiling back down to the additive law of exponents. So why is it true that, say, 3 to the negative second is equal to 1 over 3 squared? Well, the annoying answer is because it has to be. The more explanation answer is because of the following. 3 to the negative second times 3 to the second. If you multiply those together, what do you do with the powers? What do we do with the powers? We add them. What's negative 2 plus 2? And what's 3 to the 0? Yeah, it's 1. So then if 3 to the negative second times 3 to the second is equal to 1, we can divide both sides by 3 squared and say that, oh, the 3 squareds cancel over here, and we end up getting 3 to the negative second is equal to 1 over 3 to the positive second. And that's true no matter what your power was, right? If I said, something silly like 4 to the negative 17th power, well, I could then say, we know that 4 to the negative 17th times 4 to the positive 17th is equal to 4 to the 0th, and then divide both sides by 4 to the 17th to get 4 to the negative 17th equals 1 over 4 to the 17th power. So whenever you have something to a power and you want to move it from the bottom to the top, you always change the sign, or from the top to the bottom. Usually usually we're going both ways. Sometimes you like to write it like, well, definitely, I would prefer, well, that's a terrible example, James. If I had something like the previous problem, right, I definitely want to write it like that so that I can then use the chain rule the power rule version of the chain rule to take its derivative kind of straightforward. That's why we're doing that, so that we can write it as just something to a power as opposed to 1 over something to a power. We could have alternatively used the quotient rule here, but I didn't think that was a good idea. Usually, if our denominator is just something to a power, we usually try to bring it up to the numerator. So hopefully that answers your question. Yes. How much have I got? Okay, yes. So what I really want to say next is that this idea of differentiating the outer function, leaving the inside alone, and then multiplying by the derivative of the inside is valid for not just something to a power, but actually any type of function. So I'm going to show you one example and actually kind of hopefully make you believe it. And then we're going to do some other examples where it's less easy to believe, but you're going to be like, well, we saw it one time, so it's okay. So I'm going to tell you the following thing. It's true that the derivative of sine of some stuff, well, the derivative of sine of x is cosine of x. The derivative of sine of some stuff is going to be cosine of that stuff. And what do I have to multiply by? Right, the derivative of the stuff, which in this case is just 2. And sure, that seems plausible, but I would like you to really believe it. So I'm going to show you an example. I'm going to show you graphically how this works out. So we're going to graph a few things. Where'd my red pen go? Sure, there it's right in front of me. So first we're going to graph just sine and cosine. And I'll remind you, the way we found or showed that the derivative of sine was cosine was graphically. So we're going to graph sine of x first. Don't worry, it's all going to come together. And below it, we're going to graph the derivatives. So first, y equals sine of x. Let's make our period 2 pi. And half, each of those in half. 10 and a half, each of those in half. So sine of x, again, I'm graphing sine of x first, has the usual shape. Starts at 0, 0, and then at pi over 2, sine of pi over 2 is 1, and then at pi, sine of pi is 0, and then at 3 pi over 2, sine of 3 pi over 2 is negative 1, and then we get back to 2 pi. Try to make this look real nice. It's always a good way to ensure it's going to look terrible by saying, I'm trying to make this look really nice. And I always, okay, good. I made it. All right. So there's my graph of sine. And as we saw before, we graph the derivative by finding the slopes of the tangent lines. So the slope of the tangent line at the origin is 1. And the slope of the tangent line at pi over 2 is 0. Slope of the tangent line at pi is negative 1. Slope of the tangent line at 3 pi over 2 is 0. And the slope of the tangent line at 2 pi is back to 1. And so we can see, and I know we saw this before, but we're seeing it again, that for sine of x in blue, the derivative is cosine of x. Okay, so now we're going to graph sine of 2x. What does the 2 do to the sine function for sine of 2x? Well, y equal to sine of 2x has a shorter period. It has a period of 2 pi divided by 2, which is just pi. So for the sine of 2x graph, we're going to get the whole cycle of going up and then back to the middle, then down and then back to the middle in half the x distance. So check this out. I'm going to zoom in a little bit here. So from 0 to pi, we're going to get a full cycle of the sine function, or a full period. So at 1/4 of the way there, we're going to go up to the top, and then half the way back to the middle, 3/4 of the way down to the bottom, and all one full cycle back to the middle. So it's going to look like this. And then it would repeat itself again. In fact, here's a fun fact. I think it's a fun fact. Whenever someone says you're graphing something like sine of 2x, another way to think about that too is you're just getting 2 whole periods in the length from 0 to 2 pi. Or if you're graphing sine of 5x, you get 5 whole periods from 0 to 2 pi. It's kind of neat. All right, but now here's where the fun stuff happens. Or at least the interesting thing that's going to make you believe just a little bit more that the chain rule really does work for any function. If I'm going to graph the derivative of this, now let me ask you, at the origin, which of those functions has a steeper tangent line? The blue one or the red one? The red one is for sure steeper, or at least different, right? Those two functions do not have the same tangent line with the same slope. And I will tell you the slope of the tangent line for this red curve right here, the slope of the tangent line is 2. And then at pi over 4, the slope of the tangent line is 0. And then at pi over 2, the slope of the tangent line is -2. And then at 3 pi over 4, back to a slope of the tangent line being 0. And then at pi, the slope of the tangent line is back to being +2. So check it out. When we graph this, it looks like a cosine function. It looks like the cosine function has also had its period squashed by a factor of 2, but it's also been vertically stretched by a factor of 2, which means that our derivative here in red, it's not just cosine of 2x. That would have a period of pi. It's 2 times cosine of 2x to have an amplitude of 2. But that is exactly what we expected the derivative of sine of 2x to be using the chain rule. It's cosine of our stuff times the derivative of our stuff. So I know it's kind of a lot just for one example, but hopefully that at least a little bit better shows you that, oh yeah, this idea of the chain rule works for any type of function. And it does. So let's say a couple more things in the last 6 minutes we have here. So, chain rule in general. That looks very important. So here's how I would write it. The derivative of f of g of x, a composition of functions. It's the same thing I said before. What did I say before? I said you take the derivative of the outer function. So it's going to be f prime. You leave the inside stuff alone. So it's f prime of the inside's unchanged. But then what do we have to multiply by? The derivative of the insides. There are other ways of writing this, but this is probably the way I like to write it. I think this is the best way to think of it. Not that there aren't other good ways to think of it, just I feel like this makes the most sense a lot of the time. So let me write down a few things here. Yes. So yeah, let's go back to, we're going to talk about the functions we know one more time. And then the chain rule versions. So here's what we have so far. Up until today, we knew that, for example, the derivative of x to a power was that power times x to the power -1. The derivative of e to the x is e to the x. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. And the other weird ones here. The derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x I don't know why I wrote those to the left there. I think I was planning for more space because I was thinking about the derivative. It's negative cosecant x cotangent x. And then we have the chain rule versions over here. So, oops, sorry, you can't quite see that. If instead of, so here's all I'm going to do. In every one of those functions, I'm going to replace the x with stuff, and then the derivative, in addition to replacing the x with stuff, I'm going to multiply by the derivative of the stuff. So for example, if I have stuff to some power, the derivative is that power times stuff to the power minus 1 times the derivative of the stuff. If my function is e to some stuff, the derivative is going to be e to the stuff multiplied by the derivative of that stuff. If my function is sine of some stuff, the derivative is going to be cosine of the stuff times the derivative of the stuff. And the list goes on, right? It's just the same thing every time. If my function is cosine of some stuff, the derivative is negative sine, leave the stuff alone, multiply on the outside by the derivative of that stuff. And yes, I can write this 4 more times. If the function is tangent of some stuff, your derivative is secant squared of the stuff multiplied by the derivative of the stuff. So in case it hasn't been clear yet, I want to make it really extra super duper clear. Whenever you're using the chain rule at the end of the process, you are always multiplying by the derivative of the argument of the function, or the stuff, as I will almost always call it. If your function is cotangent of some stuff, your derivative is negative cosecant squared of that stuff, multiplied by the derivative of the stuff. And the last two, which are kind of funky. So if you're taking the derivative of secant of some stuff, the stuff shows up twice. You're going to get secant of the stuff times tangent of the stuff, then multiply by the derivative of the stuff, still only once. And lastly, if you had cosecant of some stuff, your derivative would be negative cosecant of that stuff times cotangent of that stuff. And then after all that, multiply with the derivative of the stuff. Whew. We'll definitely post this on Canvas as well, so you can see it there if you don't want, if the picture here doesn't turn out great. And then I will just say 2 quick examples here. If I took, say, the derivative of e to the x cubed minus cosine of x, well, the derivative of e to the stuff, here's what I really actually said. I don't actually say that. What I really think is, what's the derivative of e to the x? Oh, it's e to the x. So then e to the x, I replace with stuff. I said, okay, if the derivative of e to the x is e to the x, then the derivative of e to the stuff must be e to the stuff. But then I still have to do what? I still have to multiply by the derivative of the stuff, which is 3x squared minus negative sine, so plus sine of x. Or for one more example, if my function is, say, secant of x to the 6th power, I know my derivative is going to be, well, again, what I'm actually saying in my head is I know the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of that is going to be secant of that times tangent of that, then multiplied by the derivative of that thing. So my derivative here is going to be secant of my stuff times tangent of my stuff. Then we multiply by the derivative of the stuff. So whenever your argument is any more complicated than just x, you're thinking of the original formula, replacing it with whatever that more complicated thing is. And then at the end of the process, we're multiplying by what? The what? Not the stuff, the what of the stuff. The derivative of the stuff. Very important distinction. You're always multiplying by the derivative of the stuff at the end. All right, I'll see you all on Thursday. Yeah, I will see you all Thursday. I think my other class, yeah. I have a doctor's appointment at 2:30 on, yeah, I'll see you all on Thursday. I will not see my other class on Thursday. So you got your name on the sign-in sheet wherever it ended up at.